Consider rolling a die twice and recording the sum of the die. The random variable x is the sum of the two die. X can take the values 2 through 12. Notice you should be able to do this without the calculator. It's going to be some fun fractions, might stretch your brain there a little bit, but a calculator is not needed on this problem, though if the fractions get hairy enough later, you might wish you had one, but you don't need one. First question says find the PMF. Now, previously I gave you the PMF. This time I'm asking you to find it. I want to work through this just because I want us to get comfortable with assigning probabilities. This is a concept that we're going to have to do throughout the course. Remember that a PMF is just a table with x's and then all the possible values. I've already told you what they are, 2 through 12, which makes sense, right? You can't roll two die and sum up the value and get 1. You can't roll two die and sum up the values and get 13. There's two six-sided die, of course. And so we're going to have a table of x's and then 2 through 12, and then we've got to pair them with a probability. So what is the probability that I get all these things? And you say, well, I don't know. And you might think to yourself, well, maybe they're all equally likely. And this is where we have to be careful. It's equally likely that we get the numbers 1 through 6 on each of the die, but that does not mean it's equally likely that you get a 2 as you get a 6 as you get a 10, right? It's more likely you get a 6. It's more likely you get a 7 than it is you get a 10 or an 11 or a 12. And if you want to stop and pause and think that through, you can just work that out and hopefully make it make sense. And we're going to take that a step further in finding the PMF as I walk us through this. The probability that I get a 2 when I roll two die is, as we talked about last chapter, how many different ways can I make a 2 happen? Divide by how many different ways can anything happen? It's successes over trials. It's how many ways can I be successful over how many different total options are there? That concept's going to come up over and over. You need to be comfortable with that. Okay, so this might feel a little painful here, but I'm doing it because you need to be able to do that, to understand that concept and apply that concept, because we're going to get in the middle of complicated problems, and I'm going to need you to feel very comfortable with saying, oh, I know that this can happen 5 different ways, and 2 of them lead me to a success. So my probability is 2 out of 5. And so we're just going to work through that with 2 through 12. How many different ways can I roll a die and I get a 2? And the answer to that is 1. There's only one way that can happen. It's get a 1 on the first die and get a 1 on the second die. And go to the next one. Okay, 3. How many different ways can I get a 3? So I can get a 2, 1, or I can get a 1, 2. And you say, no, wait a minute, that's the same thing. No, it's not. Remember, when we talk about outcomes, we say that the order matters. Getting a 2 on the first die and a 1 on the second is different than a 1 on the first and a 2 on a second. There's 2 ways I can get a 3, a 2, 1, and a 1, 2. Then I go to a 4. How many ways can I get a 4? Say we can get a 2, 2, 1, 3, 3, 1. You don't put 2, 2 twice because that's the same thing. If I get a 2 on the first one and a 2 on the second one, that's not different than a 2 on the first and a 2 on the second. Does that make sense? How that is the same thing, but a 3, 1 is different from a 1, 3. So there's 3 ways I can get a 4. And at some point, if you want to pause and work through the rest, you can. If not, I'm going to keep talking through them, but you could figure the rest of this out on your own. It's just going through the same thing over and over again. How many ways can we get a 5? Right? We can get 1, 4, 4, 1, 2, 3, 3, 2. How many ways can I get a 6? Let's say 1, 5, 5, 1, 4, 2, 2, 4, 3, 3. There's 5 different ways. How many ways can you get a 7? Say 1, 6, 6, 1, 2, 5, 5, 2, 4, 3, 3, 4. There's 6. And at some point, again, if you need to pause and work through this and write this out, you can. For an 8, you'd say I can get a 2, 6, 6, 2, 5, 3, 3, 5, 4, 4. So there's 5. And you may say, well, but what, you might, well, we missed a 1, right? But you can't have a 1, 7, right? Just a 6-sided die. So 1, 7 isn't an option. There's only 5 ways you can get an 8. You can get a 9. We can get a 5, 4, 4, 5, 3, 6, 6, 3. There's 4, 10. You can get 5, 5, 6, 4, 4, 6. For an 11, there's 2 ways. It's 6, 5, 5, 6. And then for a 12, there's 1 way. That's 2 6s. This is a symmetric distribution, which is kind of neat. And you would say, okay, well, that's great. I found how many ways I get each one of them. How do I get a probability? Because I need the f of x. That's the PMF is the f of x part of that, which is a probability. Well, as we said, it's how many different ways lead you to success for that outcome, divide by how many different ways are there things can happen in total. And if you were to add up all those different dice outcomes we talked about, you get 36. There are 36 different options. And so the probability you get a 2 is 1 out of 36 because there's one way to get a 2 and there's 36 different options. For a 3, that's 2 out of 36. There's 2 ways you can get a 3 out of the 36 options, right? So I want you to get comfortable with this probability concept of how many different ways got me to success, divide by how many different ways are there total, right? And then we keep going, 3 out of 36, 4 out of 36, etc. And you should be able to fill in the table. Now I've reduced some fractions. You might want to work with the unreduced fractions. I work with the reduced fractions because that was kind of ingrained in me, but it makes the math easier if you do the math with the unreduced fractions, because the common denominator, you've already found it, so we don't have to re-find it again. And you can verify that this is a probability distribution. There are no probabilities less than 0. There are none greater than 1. And if you were to add them all up, you would get 1. How would I add them all up? I could simply say, add up all of those numbers. And again, we add fractions. We keep the denominator the same. We add the numerators. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 should get you back to 36. That's how we found that the denominator was 36, because we said that there were 36 ways. So we add up all those numbers. We should get 36 over 36. That makes 1. So find the expected value. Now you should feel pretty comfortable with this. We just worked an example. Again, if you want to pause and work through it yourself, now would be the time to do so. But we're just going to do the same thing. We're going to take all of those x's and multiply them by their f of x's, and then add them all up. As we discussed, I'm working with the reduced fractions. I don't recommend that unless you just love it. It'd actually be easier if you did the out of 36s, because then you wouldn't be dealing with all these weird denominators here and trying to figure out what they add up to. In the end, you get 7. And I think that was an awful lot of work just to get a whole number. But that shouldn't be too surprising to you if you put all the pieces together. And I want to remind you of what we talked about in chapter 2 when we talked about distributions. We said if we have a symmetric distribution, the mean, the median, and the mode will all be the same thing. And if you look up at your notes and you look at that distribution and you were to make a graph out of that, notice that the bars for 2 and 12 would be pretty small, being 1/36. The bars for 3 and 11 would go 1 unit higher, etc. And we would have a perfectly symmetric distribution. And the mode, being the peak of that distribution, would be 7. And if we have a symmetric distribution, the mean, median, and mode would be the same. And in this case, the mean is 7. So that should make sense to you. Now, if we have any skewness, we can't say that. But in this case, we have a perfectly symmetric distribution. And so the mean just turns out to be 7. So put those pieces together and think through that, make sure that makes sense to you. I don't have you find the standard deviation here. It gets needlessly complicated, but we're going to do some probability work here. We're going to start off with what's the probability of rolling a 7 or an 11. This is a little bit more complex than the probability question in the example earlier, but not by much. What I'm looking for you to do here, what I want you to get really comfortable with, is writing out probability notation. This is an or, and so I'm just going to write out probability x equals 7 or x equals 11. Now before, remember we said we could have probability A or B, and that was that case where A just happened to be, you make it to class on time. There's no number with that. But now that we're dealing with random variables, we have a variable letter, in this case x. It could be y, it could be anything. We use x a lot just because we like x in math, but it could be anything. It doesn't really have to be that letter specifically. It's just a letter, and then equals whatever number we're talking about, because all of the random variables all have, they're all numbers, right? That's what a random variable is it mapped those words, those outcomes, to numbers. So we're going to write probability x equals 7 or x equals 11. So we get comfortable with this probability notation. We talked about our addition rule. We can just add when we see the word or, as long as the events are mutually exclusive, meaning they can't happen at the same time. You look at this and you say, duh, I can't roll 2 die and get both a sum of a 7 and an 11. That's not possible. It's either a 7 or an 11 or something else, but it can't be both. So I just have to add those probabilities. So I'm going to rewrite that as probability x equals 7 plus probability x equals 11. Now I can replace those with the fractions in the table. When you say, now wait a minute, how does it make sense? This goes back to what we talked about at the very beginning. You need to understand that when we see probability or f of whatever the number is, those are synonymous. So probability x equals 7 is f of 7, probability x equals 11 is f of 11, just means go back to the table and write f of 7 and f of 11, replace those with those numbers that you found, then do the addition, and you can get the value of 2/9. What we walked through right there is the general way that a lot of the problems are going to work in this course, and that you're going to need to start off with first, what is the question even asking? And sometimes it's super simple and it's one step. Boom, we're done. Sometimes, like this one, it's a couple steps. I've got to take that and I've got to say, I can't do anything with that. I have no formula. I have no table that works for this, but I can rewrite the probability statement into something that's easier to work with. And so I get a lot of questions that'll say, well, how do you know what to do next? Your thought process is always to focus on how can I move the problem forward? Okay, you're always thinking, how can I move the problem forward? And then the follow-up question becomes, well, how do I know when I'm done? When you've answered the question. Use your critical thinking skills and ask yourself, have I answered the question? If you've answered the question, you're done. Okay, always move the problem forward, always stop when you've answered the question. So I started off with this probability statement here with this or, and I have no table that helps me with ors, but I have a formula that translates this or to something else. So I move the problem forward by rewriting it in a different way. We're gonna have to do that a lot. We're gonna have to rewrite the problem a different way. Because I can't do anything with this, but if I rewrite it, I can do something with this because these are the values from the table. Then I plug those values in the table. I'm not done here because I haven't found a probability, but once I add them together, boom, now I found the probability. I know to stop because it says find the probability. I gave a probability. Do I know it's the right probability? No, at some point I have to trust that I did I found the right values, I did the right math, etc. But at least I know I've answered the question. You don't stop here because that's not a probability. A probability is a number between 0 and 1. This is not a number between 0 and 1. This, not a number between 0 and 1. This is a number between 0 and 1. Moving forward, find the probability of rolling at least a 10. Same idea as the previous problem. If you think you know where to go, pause now and work through it. First thing I want to do though is just write out the probability statement. You're going to hear me say that a lot. We're going to write out a probability statement. So I'm going to translate that into symbols. That would be the probability x greater than or equal to 10. I have no table that translates greater than or equal to's. I have tables that have f of x, and f of x is the same as probability x equals something. Notice this is not x equals 10, right? If this says probability x equals 10, boom, just go to the table. This isn't what the table gives me. The table does not give me greater than or equal to's. So it's just like the last problem. I have to say, okay, I can't just get there. I have to do something different. What do? I need to rewrite this in a different way. Well, and you may say, well, how do I know how to rewrite it? Well, we know kind of where we want to get to, right? We know we want to get to a bunch of probability x equals somethings because then I can go to my table. So I don't know exactly where I want to get to, but I have an idea which helps me go forward. And I say, let's just think about what are the possible options that are greater than or equal to 10? Just from an English standpoint, what's the what are the values that I could roll that are at least 10? I could say, well, that's 10 or 11 or 12, and notice what word I use there, or, which means add. So I'm going to rewrite this as that's the same as the probability x equals 10 plus probability x equals 11 plus probability x equals 12, because greater than or equal to 10 means 10 or 11 or 12, or it means add. I can't get them all at the same time, so I have no subtraction, like we talked about in the addition rule. And then, as we talked about before, once I have these or equal to's, I just go to the table, plug in those values, add them up, and then I get to that probability of 1/6. And then the last one, find the probability of rolling a one same thing. Write out the probability statement. Probability, this is x equals. And how do I know it's equals? How do I know this is greater than, right? How do I know this is an or, right? And this one, the word or is there. That's pretty straightforward. This one, at least, that means greater than or equal to. This one doesn't say more than, less than. It just says, it talks about this one specific instance that's an equal to, right? And you might look at your table and say, well, I don't have a one there. And that's kind of the point. Anything that's not possible, remember, it's probability. It's always equal to 0. I could also write this as f of 1 equals 0, because probability x equals 1 and f of 1 are synonymous statements.